Welcome back. I have a function here that produces this line according to y squared equals x cubed. And now, your job is to find the centroid of this line using the x and y coordinates. So now we have to work in 2 dimensions. You have to find x bar c and y bar c. I would like you to try it by yourself first and then see the solutions in the next video, but I will give you a hint. You can take a differential element here, dl, from this line, and you can form a differential right triangle out of it where dx and dy are the other 2 sides of it. Then, according to the Pythagoras theorem, you can say that dl equals square root of dx squared plus dy squared. Then I can take this expression and multiply it by dx over dx, which would be 1. So dl times dx over dx equals, and then I do the same thing on the other side. I can put this dx over dx inside my square root, then it will be squared, and then I will have the rest of it. Then I can open the parenthesis. Now this here, it will be 1. However, I will rearrange the second term differently. I will have dx squared plus dx squared times dy squared over dx squared. I can now factor out dx squared. Then I can take it out of the square root, and this is my dl. I have this relationship here. And then I can do the same thing with dy's. Just like here I multiplied dl with dx over dx, I can multiply it by dy over dy. That will give me this expression. Then I will have it in this form, or in this form, or simply in this form, which is my dl. So that's the relationship. And so with these 2 equations that you have here, see if you can find your x centroid and your y centroid. For this one, I also suggest you to use Wolfram Alpha Integration Calculator. Thank you very much. Welcome back. So let's now find x bar c and y bar c. Let's now find the centroid for this line. First of all, if your function is y squared equals x cubed, then that means that y equals x to the power of 1.5, because you would simply square root both sides. The differential element dl has an x and a y distance. Essentially, the total length of the line would be L equals, and then you sum up all the dl's as you integrate through the line. You continuously add up all the dl's, which is what an integral does. And then, using the integral, you start continuously adding up x times dl, like this. So this integral here, it will give you the length of the line, and then with this integral, you sum up all the products of x and dl. We can call it mly, because this x is the distance between dl and the y-axis. Again, it's not a moment, it's simply an integrated product of a dl and its corresponding x. And so in that case, you can have a relationship where your length times your x centroid equals this mly. In that case, x bar c equals mly over L, and so you will have the integral from 0 to L, x times dl over, and then this integral, which is this one here. And then you will do the same thing with the y dimension. This dl here, it has a y dimension. That's the distance from dl till the x-axis, and so you can have a product y times dl and then you integrate that from 0 till L. With that, you get the total integrated product of a dl and its corresponding distance from the x-axis. We can call it mlx, and now we can say that L times y centroid, it equals mlx. So the y centroid equals mlx over L, or simply this integral over this integral. And so we had two expressions for dl, this one here and this one here. Since you know that x equals 1, then you also know that y equals 1. That's where the line ends, at x equals 1 and y equals 1. You can see it from this function. Y equals 1 to the power of 1.5, that gives you 1. And now since this is your function, y equals x to the power of 1.5, then we know that dy over dx, that's 1.5 times x to the power of 0.5. And now if I want to express x as a function of y, then it would be x equals y to the power of 2 over 3. That's because y equals x to the power of 1.5 is the same like x to the power of 3 over 2, and then here you would simply put 2 over 3 here as well, and here as well. Here the 3's cancel out and the 2's cancel out, so you will have x to the power of 1. And so now we can have dx over dy, and that would be 2 over 3 times y to the power of minus 1 over 3. Thus, if I take this expression, where I have dl that contains your dx, it will be 1 plus, and then dy over dx, that's this expression, but you have to square it, so you will have 1.5 squared, and then you will have x to the power of 2 over 2, and then you will have dx here. In other words, you will have this expression, and now you will take the other expression, dl that contains dy, this one here, you will have square root of dx over dy squared, which is this expression squared, so you have 2 over 3 to the power of 2 times y to the power of minus 2 over 3, so that's this expression squared, plus 1, and then I have here dy, and so I will have this expression. And now, this here, it's my x bar c, so I will have an integral from x equals 0 till x equals 1, and then x times, and then all this divided by the integral, and then you have this. And notice that now, instead of L, we have x's here, because instead of dl, we have dx. And so if I put all this in Wolfram alpha, then I will get this number here, 0.5457 meters. And then y bar c, that would be this division here, so you have the integral of all this divided by the integral of all this, and if I put the entire thing in Wolfram alpha, then I will get 0.4465 meters. So that's what I get. X bar c is approximately 0.546 meters, and y bar c is approximately 0.447 meters. And that means that at this point, you have the centroid of this line. Now, if the density and the gravitational acceleration g are constant, then you already know that your centroid will equal your center of mass, and that will also equal the center of gravity. However, if they are not, then that would change the result, of course. you would need to have the density of the line per unit length, per dl, so something like rho L times dl, and then for the force of gravity, you would have something like G times rho L times dl. That would be your differential mass, and that would be your differential force of gravity. And so you would simply form similar integrals, but with G and rho L that would change with your x and y coordinates. The integration would be more complicated, but again, you don't have to do it by hand. You can simply use your online integration calculator. Now you might be wondering why that centroid is not on the line itself. In certain cases, the centroid is not on the object. You can think of a circular rod, in which case, due to symmetry, the centroid would be in the middle of the circle. However, in the reality, there is nothing there, only air. And in our case, we have the same thing. Due to the shape of the line, the centroid is slightly off the line. It's not exactly on the line, but it's slightly off. Thank you very much. Welcome back. I have a cube here. Each side of the cube is 1 meter. This cube has a mass, but the density of this cube varies. In other words, its mass distribution is not uniform. The mass density function is rho equals x plus y plus z plus 1, and that's in kilograms per cube meters. You can see that at the origin, when x, y, and z are all 0 meters, your density is 1 kilogram per cube meter, and it increases the further you go from the origin. In this location here, you will have your maximum density. In this location, x, y, and z are all 1 meter, so you have 1 plus 1 plus 1 plus 1, and that's 4 kilograms per cube meter. Now, in the cube, we can define a differential volume. For example, you have one differential volume here. We can call it dV, and it has three sides: dx, dy, which is this side parallel to the y-axis, and then dz, which is parallel to the z-axis. And of course, dx is parallel to the x-axis. And so your differential volume, it's dx times dy times dz. That differential element is located at some kind of x, y, and z meters. And now, the task is to find the centroid, center of mass, and center of gravity inside this cube. You can assume that g is constant, which is 9.81 meters per second squared. So try it out by yourself first, and then see the solutions in the next video. Thank you very much. Welcome back. Let's now find the centroid, the cm, and the cg for this cube. First of all, even though the density of the cube varies, remember, centroid is a geometric center. So the centroid of the cube is very easy to find. It's at x equals 0.5 meters, y equals 0.5 meters, and z equals 0.5 meters. So it's right in the center of the cube. So x bar c equals y bar c equals z bar c equals 0.5 meters. That's your centroid. However, since the density of the cube varies, obviously the center of mass and the center of gravity are in a different place. First, let's find the mass of the cube. You have a differential mass element in the cube, which is called dm, so it belongs to this differential element. This dm can be written like this: the density times dv. So dv is the differential volume of this differential element inside the cube. Alternatively, you can write it like this: the density times dx times dy times dz. It also makes sense in terms of units. This is for the density, and then the volume has meters cubed. You cancel out meters cubed, and your dm has kilograms, so it makes sense. And so the total mass of the cube, you get it when you sum up all the differential masses. Or you can write it out like this, or you will simply have a triple integral. Instead of density, I'm gonna write this function. So this is my density, and then I have dx, dy, and dz. And since I have dx here, it belongs to the most inner integral. Therefore, in here, I will integrate from x equals 0 till x equals 1 meter. Then here I have dy. It's my middle integral. So in here, I will put from y equals 0 till y equals 1 meter. And then finally, I have dz here. That's my most outer integral. I integrate it from z equals 0 till z equals 1 meter. And now we have to evaluate this triple integral. Let's do it in 3 parts. We first evaluate the inner integral, then the middle integral, and then the outer integral. It's pretty much what we did with double integrals. It's just now you have one integral more. And so first I evaluate this integral. I can rewrite it like this. Remember, since we only have dx, we treat y and z as constants, so they go out of the integral. So this will be its evaluation, and this will be its final result, y plus z plus 1.5. Then, in the second part, I will have this integral with dy, so I'm integrating along the y direction now, and this one here, that's this result here. So you can write it out like this. This will be the evaluation of these integrals, and in the end you will get this final result, z plus 2. And then finally, this will be our third integration along the z direction. We can write it out like this. This will be its evaluation, and in the end you will have 2.5 kilograms. And there you go. You have the mass of the cube. It's 2.5 kilograms. That's the entire mass of the cube. And now, in order to find x bar cm, which is the center of mass of the x dimension, we need to take a differential mass and we need to multiply it by its x location. And then we have to integrate all that, because we have to take every single differential mass in this cube and multiply it by its corresponding x value, and then we have to sum up all these differential products together with this integral. And we can call this integrated product myz. Again, it's not a moment, it's an integrated product of a differential mass and its respective x value. And the reason why I put here yz is because this x, it essentially tells you the distance between your differential mass and your zy plane. Another way to represent this integral is like this. You still have your x here, but instead of dm, you will have this expression. So rho times dv. But of course, by the end of the day, you will end up with a triple integral where you will have x times, then this is your density, dx times dy times dz. Here you go from x equals 0 till x equals 1. Then here you will go from y equals 0 till y equals 1. And here you will go from z equals 0 till z equals 1 meter. And now you have to evaluate this integral. And the way you do it is exactly the same like we did it with this previous integral. You will have your inner integral, middle integral, and outer integral. If you don't want to do it by hand, then you can go to Wolfram Alpha. Then here you have your definite triple integral. Then you will have these fields to fill in. I'm going to have here dx, dy, and dz. Then for dx, I will have 0 here and 1 here. And then the same thing for y, and the same thing for z. And then here I will write x times, and then this is my density. Now I will press here, and there you go. Your result is 4 over 3. So let me write it here, 4 over 3. And now we had meters here and kilograms here, which means that we have 4 over 3 kilograms times meter. So that's your MYZ. And now what we have is this. We have mass times x bar cm, and it equals MYZ. So x bar cm, it's MYZ over the mass of the cube. So you have 4 over 3 kilograms times meters over 2.5 kilograms, or in other words, 5 over 2 kilograms. So I can write here 5 over 2 kilograms. The kilograms, they get cancelled out, and you will have 8 over 15 meters. It is approximately 0.5333 meters. So that's your x bar cm. Then we also need to find y bar cm. For that, we need to take our differential mass and we need to multiply it by its corresponding y direction. So for this differential element, this y is the distance between this differential element and the xz plane. And I have to do it for all the differential masses. I have to multiply all differential masses by their respective y distances, and I have to sum up all these products. In other words, I have to integrate them. And since y is the distance between the dm's and the xz plane, I will call it mxz. And then of course you can replace dm with rho dv. In the end you will have a triple integral where you have y times the density times dx times dy times dz, and essentially you have the same story. If you calculate this triple integral, you will again get 4 over 3 kilograms times meters. It's not very hard to do it by hand, but if you don't want to, then you have Wolfram alpha. And so the total mass of the cube times y bar cm, that's this mxz, and so y bar cm, it also equals 8 over 15 meters. You get it if you divide mxz over the mass of the cube. As you can see, y bar cm is the same like x bar cm. And finally, we have to find z bar cm. In order to do that, again, you take your differential mass and you have to multiply it by its corresponding z distance. So that tells you how far your dm is from the xy plane. And then you do it for every single dm inside the cube. And then you integrate the product. And then you will get mxy. Then we can rewrite it like this. In your triple integral, you will have z times the mass density times dx, dy, and dz essentially it's the same drill, and it will again give you 4/3 kilograms times meters, and so you will have the mass of the cube times z bar cm, that's mxy, and then z bar cm, it's mxy over the mass of the cube, and that's also 8/15 meters. And there you go. You know your center of mass. This point here, it's 8/15 meters. That's your x bar cm. Then this point here, it's also 8/15 meters. So that's your y bar cm. That's on the y-axis. And then this point here, that's also 8/15 meters. That's your z bar cm. And so that means that this point here at x, y, and z equal 8/15 meters, this point is the center of mass of this cube. So if you apply a force exactly to this point, then this cube will accelerate in the same direction, but the cube will not rotate. And also, because of the fact that the density inside the cube is not constant, the centroid of the cube and the center of mass of this cube are different. They are not the same. What about the center of gravity though? Well, we assumed that our g was constant. We assumed constant gravitational acceleration. Because of that, you know that your center of gravity equals your center of mass. So your center of gravity is also at x equals 8/15 meters, at y equals 8/15 meters, and at z equals 8/15 meters. Thank you very much.